this session. So welcome everyone to the Tom class. Till now, whatever we have studied in this subject is mechanisms and machines. We also understood the velocity and acceleration analysis. We understood the topic of gear and gear trains. And in today's session, we are going to start a new topic, that is gyroscope. Okay. Um, so before we jump into the this topic, I would like to give I'd like to show some small video to you. We'll watch this 3 minutes video and then we'll continue our topic. Okay. So let's try to go through this video first.
Hi there. If you're watching this video, you're probably already aware of the phenomenon of gyroscopic precession and how you can predict and calculate the effect by using angular momentum vectors. No matter how good you get at calculating these vectors, and no matter how many times you do those calculations, you might be left feeling that the spinning wheel demo seems totally amazing and weird, or that these vector explanations are completely unintuitive. I sure did. So I made this video to share how I intuitively understand gyroscopic precession. We're going to start out considering satellites in orbit, but don't worry, we'll be back to the bicycle wheels soon enough. If you've played Kerbal Space Program much, this will probably be even easier to understand. So here's a single satellite in a perfectly flat circular orbit. What happens if we push up here and push down here? To be more specific, we're going to push up and down on the satellite as it passes these 2 points. If you forget that the satellite
I think screen share got ended. Let me share again. Um,
as it passes these 2 points. If you forget that the satellite is in motion and just imagine that its orbit is a giant hula hoop, you would expect the orbit to tilt like this. But that
okay. Are you following till this? So we have a satellite revolving around the planet, and this blue arrow indicates that we are trying to apply force um, at these two locations. Okay, I'll just go a little back. Um, yeah, so when satellite comes to this particular location at downward side, we are applying upward force, and when it goes back side of the planet, we are applying a downward force. So what we expect is uh, what they are showing now. So just
points.
I'll resume it.
If you forget that the satellite is in motion and just imagine that its orbit is a giant hula hoop, you would expect the orbit to tilt like this. But that's not what actually happens. Let's think about the satellite again. As it passes this point, we push up on the satellite. Pushing up on the satellite doesn't cause it to teleport upwards and then continue moving in the same direction. It just gets sent flying in a different direction. And if you trace out the path that it takes, the orbit is tilted like this. Now keep in mind that the forces we applied on the satellite were equal and opposite, so they combine to form a twisting force around this axis. But we can clearly see that the orbit was tilted around a completely different axis. Now before we continue, make sure you're completely comfortable with this idea. Pushing up on the satellite here causes the orbit to tilt like this. Feel free to pause the video, rewind, or even go ahead and play Kerbal Space Program until you get the idea. Now, let's look at the classic example of a bicycle wheel suspended from a rope. A bicycle wheel is obviously...
So what we have seen till this is if we have a satellite and that is rotating around a planet, and if we apply force at a certain location, so that we are trying, so what we are doing is we are applying a load in perpendicular direction to the axis of rotation. So basically what we have understood is it is tilted in some other direction. Okay, it is tilted in some third direction. So let's try to um, the same example. Now they are giving with a bicycle wheel. They are just correlating this bicycle wheel example with the planet and the uh, a satellite example. Okay, and when we study these things in let's say theoretically in this chapter, we will try to understand how this effect uh, applicable for aeroplanes, how this effect causes um, this gyroscopic effect looks like in sheeps or four wheelers or two wheelers, because in all these cases we have some rotating part. So I hope till now you might have understood that this gyroscopic effect is associated with rotating body, right? So wherever we see the rotating body, like majorly bicycles, then cars, or two wheelers, or let's say um, propellers of ships, or the propellers of the aeroplane. Okay, so these are the major examples we'll be considering this chapter. So just to, because before we go into that examples, let's try to understand second part of this video.
Obviously a solid piece of rubber, but I'm going to replace it with individual balls of rubber. It makes no difference to the end result, but it makes it easier to think about. Gravity is pulling down on the wheel here, and the rope is pulling up here. These forces combine to produce a twisting force called a torque, trying to twist the wheel this way. Now this twisting force is totally equivalent to pushing right on the wheel here and left on the wheel here. Either way, the twisting action is trying to turn the wheel clockwise. Now we shift our point of view to look at the wheel from above. Does this scene look familiar now? It looks just like our orbiting satellite, except instead of just one satellite, we've got a whole bunch in the same orbit. But once again, this makes no difference. As the rubber balls get pushed up and down, they get diverted into a new path, rotating like this. Now, of course, I've made some simplifying assumptions here. In reality, the torque is applied via the bearings in the hub of the bicycle wheel, rather than via magic force arrows, and the force is probably spread out around the hub rather than applied at just 2 points. But once again, it turns out that none of this makes any difference to the end result. No matter how you apply torque
So
to a
I
rigid
am
body, the end
ending
of the
now.
satellite doesn't cause it to teleport upwards and then continue moving in the same direction. It just gets sent flying in a different.
Okay, I'm ending the video now. I hope at least some idea you might have got through this video. Okay, um, let's come back to our theory part now. If you have not understood it, no problem, you can go through the video again later. Um, you can just type in YouTube gyroscopic effect. You will get a couple of videos and you can go through it. Okay, but yeah, at least you might have understood that this effect is associated with some kind of rotating body. Okay, which is rotating in particular direction, and if you apply certain, let's say, force, or if we um, try to, let's say, change the direction, uh, it causes this effect results. Okay, so this is the basic idea. Let's go through this into the detail. So write down heading gyroscope. Okay, the definition would be like, if the axis of the spinning or the rotating body, if the axis of the rotating body is given an angular motion, okay, so in the example of let's say the satellite rotating about the earth or planet, we were giving, we are applying the force, right? So basically what we are doing, that in that we are giving an angular motion to it. Okay, so if axis of the rotating body is given an angular motion about an axis perpendicular to the axis of the rotation, about an axis perpendicular to the axis of spin, okay, an angular acceleration An angular acceleration acts on the body about the third perpendicular direction. Okay, about the third perpendicular direction, or third perpendicular axis, we can say. Yeah. Okay. So basically, in order to we can say torque required to produce this kind of acceleration is called as a active gyroscopic torque, and reactive gyroscopic torque will also generate. Okay, and the effect produced by this reactive gyroscopic, we can say, is a gyroscopic effect. Okay, so basically what we have understood is, let's take this, consider this body. Okay, whenever this body, let's say AB is the 2 point, are the 2 points, and we are rotating this body in the clockwise direction with certain angular velocity omega. Okay, so how can I represent this body into a, let's say, simple diagram using a right hand thumb rule? Okay, so whenever you are using a right hand thumb rule, the thumb denotes the direction of um, the thumb denotes the vector direction, and the all the rest of the forefinger shows the rotation. Okay, whether it's a clockwise or counterclockwise. Okay, so for example, if in this case we can clearly see omega is clockwise first. Okay, so this is rotating clockwise. If it is rotating clockwise, uh, it means you can use the figure B where omega is clockwise. Okay, the okay, uh, not sure why my video is getting ended. Okay, uh, so in the first case, as I'm saying, omega is um, basically the direction of the rotation of the rotor is in clockwise direction, and so vector AB represents here um, the length of this vector represents the magnitude of the velocity, and direction will represent the axis of the rotor. Okay, so our axis is along AB, and depending on omega, it's, you can, let's say, vary the length of this vector. And sense of rotation you can clearly see by arrow. If arrow indicates the direction of the thumb, then the rest of the finger shows the direction of rotation of the disc. Okay, so if it is rotating in counterclockwise, the arrow will be from B to A. Okay, counterclockwise. Are you following till this? Are you getting how right hand thumb rule we are using? Okay, so put your thumb towards the arrow and try to check how your fingers are. Okay, so if your fingers, if arrow is um, in this case arrow is in this direction, so your fingers will be in clockwise direction. In the second case, if arrow is in this direction, your fingers will be in counterclockwise direction. Okay, so remember this kind of figures will be using a lot in this chapter. Okay, so what, let's come back to this definition. So you, yet at least you understood axis of rotation. Here AB is axis of rotation. Okay, so if you are giving an angular motion about the axis of, okay, to this axis of rotation perpendicular to the axis of the spin. So if you're, let's say, um, applying some load here, or let's say changing this by some, let's say, some theta degree angle, okay, because of some load or something, then what will happen? Then angular acceleration acts on the body about the third perpendicular axis. So either this acceleration will be in upward direction or downward direction. Okay, so if you talk about x and y, then the angular acceleration generated will be in the third perpendicular direction, that will be the z direction. So either upward or downward, that we are going to see. Okay, and the torque required to produce this acceleration is called as an active gyroscopic torque. Okay, and basically for every action there will get a reaction, so it will have a reactive gyroscopic torque or couple. Okay, and the effect produced by this reactive gyroscopic couple, effect of this reactive gyroscopic couple is nothing but the gyroscopic effect. Okay, um, we'll try to understand this through certain examples as we move in this chapter. Okay, as of now I would expect from you is you should understand how this vector diagrams are drawn, a to b or b to a, how the omega is judged on the basis of the arrow. Okay, and whether it's a clockwise or counterclockwise, and you should know the uh, here what is active and reactive gyroscopic torque. Okay, so as like active and reactive gyroscopic torques are more or less similar to the concept of centripetal and centrifugal forces in the rotating body. Okay, so similar thing we are applying here, and wherever we are seeing the rotating bodies like aeroplanes, ships or automobiles, in all these cases the gyroscopic effect comes, and that is what we'll study over this chapter. Okay, so here we have studied, let's say, three new points. What is angular acceleration? First, that part we'll study. Then we'll try to understand this active and reactive gyroscopic couple in detail when we go through some examples. Okay, so let's start with the first point, angular acceleration. Write down heading, angular acceleration. Maybe this figure would work. Yeah. Okay, so let here the rotor is rotating about the horizontal axis OX. Okay, I am showing you axis OX here, which is uh, first axis of rotation. Okay, and here this rotor, okay, is rotating at omega radian per second in clockwise direction. Okay, so I can show this omega by using this O to A vector. Okay, I hope till this it should be clear to you. I'll use a red pen. Um, yeah. O to A indicates that we are rotating or spinning this wheel on OX axis. Okay, this is O center and X is this OX axis, and the direction is clockwise. So, okay, and that is what we can see here. Okay, so if you see from this side, it is clockwise. Correct. Now, what I am doing is I am uh, changing this axis now. Okay, I'm changing this axis. So we have studied we were studying that. Let's say if you are given some angular motion to it, let's take a, we are changing the axis by some angle delta theta. Okay, so by delta theta I'm changing the axis. What will happen is the new axis of spinning will be OX dash. Okay, OX dash will be new axis of spinning. Okay, and let's say magnitude of the angular velocity is changing, because that will be more generalized case. It can remain same or it can change. Okay, so we assume more generalized case. Let's say the magnitude of the angular velocity is also changing, not just the theta, but the magnitude of angular velocity is also changing. So initially it was omega, now it is omega plus delta omega. Okay, so along this axis I would draw another vector, because that will be little longer from this or shorter depending on whether delta omega is positive or negative. Okay, in this case let's assume delta omega is a positive, so we'll get a bigger vector than the previous at an angle delta theta. Okay, and all this is happening in time delta t. So I hope you understood OA and OB vectors. Okay, OA is angular velocity, initial angular velocity, and when we have rotating this disk about, or let's say we are giving some angular motion to it by delta theta, the new axis is OX dash. Okay, and the angular velocity corresponding there will be, let's say, omega plus delta omega. So now if you join these points A and B, what that represent is that represent the change in the angular velocity of the rotor. AB represents change in the angular velocity. Okay, this, and this AB can be further split into two parts, AC and CB, and according to the vector addition, AC plus CB will be AB, right? Because we can just resolve AB into two components. One is horizontal component, another one is a vertical component. So AC here is um, the horizontal component of the angular velocity in the, and CB is a, or BC is a, or let's call it CB itself because it's going from C towards B. So CB is a vertical component. What is AC here? If you look into the details, this is your delta theta, AC and CB. I'll write them in detail now. What is AC? Can I write AC as let's say omega plus delta omega cos of theta minus omega? Can I write it like this? So this whole length minus this length will be this length, right? In order to get this length, I will subtract A, capital A, and then I'll subtract B from it, then only I will get AC, right? I hope you understood. So what is capital A? Capital A is omega plus delta omega cos of delta theta, right? And minus omega will give you the AC, right? This is your velocity. This is your component of change in the um, angular velocity in the x direction. AB is a angular velocity or change in the angular velocity, and it is, we are splitting it into AC and CB. AC is a angular velocity change in uh, x-axis. And what is the rate of change of angular velocity? Rate of change of angular velocity will be angular acceleration, right? So therefore angular acceleration is, I would say, omega plus delta omega, or limit delta t tends to 0, omega plus delta omega cos of delta theta minus omega divided by delta t. Okay, so this is how we do the differentiation. So as delta t tends to 0, what I would expect is delta theta also tends to be 0, right? delta theta will also will become smaller and smaller, and cos of delta theta will become 1, correct? Cos 0 is 1. So ultimately what we can say is limit delta t tends to 0, omega plus delta omega minus omega divided by delta t. So omega will get cancelled. So ultimately I'll write it as d omega by dt, I can say. Okay, this is the um, d omega by dt, I can say as a rate of change of angular velocity in the uh, x direction, because AC represents the angular velocity change in the x-axis. Similarly, if I say CB, how can I write CB? CB would be, now I'll rub this. CB is this, right? This length. So it is clearly simple. Omega plus delta omega sine of delta theta. Okay, that's all. Okay, this is delta theta, so this is sine component of it. Yes, correct. Sine of delta theta we can write. And now the angular acceleration. Here is limit delta t tends to 0, omega plus delta omega delta theta divided by delta t. Sorry, sine of delta theta divided by delta t. So as here delta t tends to 0, what we would expect, delta theta would also tends to 0, and for smaller angle sine of delta theta is equal to delta theta, correct? So that we know that for smaller angle sine of theta is itself equal to theta. Uh, when we go to like very close to the 0. Now if you put that into here, what we'll get is omega plus delta omega into delta theta by dt, and as delta omega is a smaller quantity, I can write it as omega d theta by dt. Okay, directly delta I'm replacing with a d now using limits, so I can write it as omega d theta by dt. Okay, so this is the angular acceleration, you can say uh, normal to the in the normal direction, or the in around the y-axis, we can say. So we have one part and we have second part. Yeah, dt, thank you. And I will add them together. I'll write in the next slide. Total angular acceleration is equal, which is represented by alpha, that is equal to d omega by dt plus omega times d theta by dt. Okay, so what is this d omega by dt represents? Change in the magnitude of the angular velocity of the rotor. Of the rotor, and omega times d theta by dt term represents change in direction of the axis of spin, because we are changing the del theta here. Okay, omega is constant, theta is changing, so change in the axis of, or change in the direction of axis of spin. Okay, yeah. Now we can say this was like a more generalized case. Okay. um, yeah, at least we understood what is what are all the components we see in the angular acceleration. Okay, so write down this first formula: d omega by dt plus omega times d theta by dt. Okay, so this was our first point. If you remember the first slide, we studied the angular acceleration. Now the two other topics are like a gyroscopic torque. Okay, whether it's active gyroscopic torque or reactive gyroscopic torque. Torque means like a couple basically. What is couple, you know, right? In um, uh, so strength of materials, you might have studied, like if we have, let's say, this kind of loading, it will create a, let's say, a moment about the axis of the rotation is nothing but the torque itself, right? So we'll use the torque here because we are talking about the rotation about the axis of the um, rotor. Okay, so basically torque is nothing but the a kind of couple itself. Now let's write down heading gyroscopic torque. Okay, gyroscopic torque. Let me check if I have any slide here to show, or just give me a minute. We need this diagram again. This diagram, so I have to uh, okay, then I think we don't have that diagram. I have to draw it. Mm, okay, let's take it. Mm, let's forget about it. We'll draw it. Mm, because here this was more generalized case. I'll explain it through a simple case now. Write down heading gyroscopic torque or couple. Okay, so let's take this, write down, draw this figure: y-axis, z-axis, x-axis. We have this disk which is rotating in clockwise direction at an omega, and we are rotating this disk by, let's say, some, we are rotating this disk, let's say, by certain angle delta omega, but we are not changing the disk speed. Okay, so whatever is the, let's say, rotation speed, that is radian per second, it's same we are keeping. We are not changing that omega value. It is still rotating at omega itself, but we are just taking a turn. Okay, or changing the um, axis of rotation by delta theta. So this is OX is your first axis of rotation. OX dash is the new axis of rotation. So how I would draw, let's say, the velocity vectors. O to A here I will represent as a, um, let's say, not, yeah, maybe an angular velocity, whether it's correct. Yes, yes, it's correct, it's a clockwise direction. The arrow is correct here. Okay, suppose we have this disk with I moment of inertia, and omega is an angular velocity, and it's initially spinning at OX dash, and then we are giving angular motion to it by delta theta, sorry, delta theta, and new axis of rotation is OX dash now, and this is all happening in delta t time. Okay, coming towards the vector diagram, OA represents the angular velocity of the rotor when rotor is rotating in OX direction. Okay, and now I'm changing it to OX dash, so OB will be new vector. Are you following? OB will be new vector. Length is itself is same omega. We are not changing the omega. Okay, OA represents the angular velocity of the vector when the axis is OX. OB represents the axis change to OX dash. Then AB represents the change in angular velocity. Okay, A to B is, we are changing here A to B. Okay, um, we are not drawing it to a straight line. Okay, um, as like it is changing. Let's say we are just changing the axis, so it is circular axis. Okay, so I'm drawing the curvature here. Okay, so this path we are taking A to B. So what is A to B? Change in the angular velocity due to change in the direction of the axis of the spin of the rotor. Okay, how you will calculate this change in angular velocity? Can you tell me? Is represented by AB, change in angular velocity. This is your delta theta. Change in angular velocity will be omega delta theta by delta t. Okay, sorry, omega delta theta. Change in angular velocity will be omega delta theta, and angular acceleration in this case would be,
Sir, I think it was not the change in angular velocity. It was change in angular moment.
no. So what I am trying to show you here is, let's say in the first case, if you come to the previous part, there we have studied two components of the total angular acceleration. The first one is because of change in the magnitude of the angular velocity, and the second case is because of change in the direction of the axis of the spin. In the latest example which I have shown, there we don't have change in the let's say angular velocity. You can clearly see there omega is was changing from omega to omega plus delta omega, so this term won't come into the picture. um, and ultimately what we'll get is omega times d theta by dt, only the second part of the uh, derivation will get. Okay, this is your angular acceleration, and this should be your angular velocity, because change in the angular velocity with respect to time will be your angular acceleration. Okay, is it clear? Yeah, now so what I was explaining you is so here let's try to understand the second and third point, that what is active gyroscopic, sorry, in the first slide itself I have mentioned here active gyroscopic torque and reactive gyroscopic torque. So these 2 points we'll study now in this figure. Okay, this A to B, if you see here, that is your active gyroscopic torque. Okay, what is active gyroscopic torque? The torque required to produce this angular acceleration is called as active gyroscopic torque. So A to B is like an applied couple, you can say, or active gyroscopic torque. And let's say similarly we'll get a reaction here. Let's call it as B dash to A dash. B dash to A dash, that is, let's call it as a reaction couple. Okay, I'll repeat. Whatever torque we are applying, or which is required to cause, or which is required to change the axis of the spin in the horizontal plane from OX to OX dash, you can call it as an active gyroscopic torque. Okay, or applied torque or applied couple. All these things are same. Okay, and what is this reactive gyroscopic torque or a reaction couple or reaction torque? It's a reaction out of it. Okay, it's a basically a result of the your action, you can say, like what we can see in centrifugal and centripetal forces when you are rotating a certain body. Okay, um, and what is the magnitude of it? Magnitude, so basically how much, whatever you are applying the active gyroscopic couple, the same value will be there for reaction couple, but the direction will be opposite. And I will calculate the acceleration torque, or the this applied torque, you can say. The torque value will be given by, I would say, I omega into omega p. Okay, what is this omega p here? Omega, we know that is where the that is the angular velocity of the disk. Okay, I also we know that is the moment of inertia of the rotor. What is this omega p? This omega p is nothing but the angular velocity of the precision. Okay, write down here. Omega p is angular velocity of the precision. Okay, and what is this? This angular acceleration, you can write it as omega times omega p itself. Okay, and you know torque is equal to I times alpha. Okay, so this is angular acceleration, you can say as alpha, and torque is equal to I times alpha, and that is why it is I times omega p. Okay, so this is how you can derive it. Delta or d theta by dt here, or delta theta by delta t, is angular velocity of the axis of the spin, and which is called as angular velocity of the precision. Okay, here this is your angular velocity of the spin. This is how, okay, you are changing um, the axis of the spin by delta theta in delta t time, and that is causing this omega p. So this is omega p basically. Okay, omega p comes here, delta, because of this rotation, and omega comes because of this rotation. Okay, about the axis, don't get confused into it. Omega is the axis of, omega is, let's say, a rotation uh, velocity or angular velocity of the rotor, and omega p is angular velocity of precision, which is um, angular velocity of the axis of the spin. Okay, our axis of the spin is changing from OX to X dash with a delta theta angle in a delta t time. Okay, so this is another formula you should know how to calculate the torque. Okay, so one is applied action torque and other was a reaction torque. So let's try to understand this action and reaction in more detail through some practical examples. So we have just gone through the formula part. Now let's try to understand the effect in reality, how it looks in case of aeroplanes, ships, four-wheelers and two-wheelers. Okay, that is the scope of your syllabus. Can I proceed to the next slide? Any doubt till this? Yeah, okay. Yes. Direction of torque. Okay. Yes. So direction of the torque, same thing. You can still use the um, your right hand thumb rule. So here, uh, the in this case, the reaction would be, let's say, counterclockwise. Okay. Yes. So in this, you can still use right hand thumb rule. Okay, and you can write the direction. Okay, you understood how I have written this direction just by using the right hand thumb rule. Yeah, the right hand thumb rule is very, very important here. So let's try to understand this phenomenon in now in planes, aeroplanes. Gyroscopic effect on aeroplanes. Okay, so we have first figure number A. Okay, what it shows? It shows aeroplane, and we are viewing from or looking at the aeroplane from the rear end, which is tail, and on front side we have a nose of the aeroplane, and on which we can clearly see the propeller is there, which is rotating in the clockwise direction first. Okay, and let's say OA here is some angular momentum vector due to the angular velocity. Okay, let's assume this. Yeah. Now, what is happening is, let's say this aeroplane takes a left turn first. Okay, this entire aeroplane is, let's say, trying to turn in the left hand side. What will happen? So basically, this axis of rotation is initially this, and now it will be this. Do you agree? You are changing it from OX to OX dash in by some angle, let's say delta theta. So same thing what we have studied before. I will write a new vector OB, which is at a delta theta angle. Okay, so I'll drop this part. This I have written just to explain you how this OA and OB vectors are there. OA vector is initial vector. Okay, and if this aeroplane takes a left turn, the angular momentum vector is shifted, and you can represent it by OB here, which is by angle theta. Okay, and what is this A to B? A is your active gyroscopic couple, because in order to change this angular momentum, you have to apply some torque, right? You have to apply some force, then only it will change. So that is nothing but the active gyroscopic couple. Okay, and this, if you see, it will be in clockwise direction. Do you agree? If you see from this side, it will be in clockwise direction. Okay, if you let's say see from this side, it will be in clockwise direction, and B dash A dash will be a um, a reactive gyroscopic couple, which is equal and opposite to AB, and we can clearly see by using right hand thumb rule its direction is counterclockwise if you view from this side. So it is like this if you see. So what will happen? The interpretation of this vector shows us that the couple acts in the vertical plane and in counterclockwise direction. Okay, so if you are seeing from this side, it is acting in a counterclockwise direction. And how you can interpret out of this, or what it indicates to us, that it will rise the nose, okay, and lower the rear or tail part of the aeroplane. Okay, this counterclockwise couple will generate only when you have upward force in the rightmost part of the let's say aeroplane, and the downward force in the uh, let's say the end part of the aeroplane. Okay, then only you will see this kind of couple. So because of this reactive gyroscopic couple, what will happen is whenever you are taking a left turn, okay, slightly your the nose of the aeroplane will get tilted up, and tail of the aeroplane will depress, okay, or go down. Are you following it? Okay, so this is how the gyroscopic effect in aeroplane looks like. So the same thing, but now let's say I'm changing the situation. It's still rotating in clockwise direction, but you are taking a right turn now. Okay, the aeroplane is taking right turn now. So think on this. OC is initial vector, same as that of OA, and now we are taking a right turn. So the new vector will be OD. Okay, OC is the initial vector, and the new vector is now OD. So what is CD? CD is your active gyroscopic couple. Okay, CD is your active gyroscopic couple, and D dash C dash is your reactive gyroscopic couple. And if you view from this side, it is in clockwise direction. So couple is like this. Okay, couple is like this. How you will generate this couple? When you have this upward reaction here and downward reaction here. Do you agree? Then only this kind of couple will generate, and or torque will generate. That is reactive um, torque, and because of this torque, what will happen is nose will go down and tail will rise. Yes, correct. Okay, nose will go down in downward direction and tail will go upward direction, because our rotor is rotating in clockwise direction and we are taking a right turn. Okay, so now let's suppose our rotor is rotating in counterclockwise direction. So this is the situation, not this. Our rotor is rotating in counterclockwise rotation. Okay, counterclockwise. Okay, counterclockwise. So if rotor is rotating uh, in counterclockwise, then whatever things we have studied uh, will get reversed. Okay, um, because in first case, this is not this figure will be replaced by this. Correct. O to E will be because now our rotation is counterclockwise. If you view from this end, okay. Okay, if you view from this end, and then if you take a left turn, okay, then this is our new axis, which is delta theta. So this is your delta theta. Are you following this figure number D? I'm just drawing the same figure in left hand side direction. Why? Because we are running this aeroplane by rotating this propeller in a counterclockwise direction. So counterclockwise direction, if you view from this left, this side, wherever I have written viewward, will be like then the arrow has to be in towards that direction. Okay, and then new axis of rotation is, let's say, this delta theta. So let's say this is also delta theta. This is point E and F, and this is your E to F active gyroscopic torque, and F2 is your reactive gyroscopic torque. Okay, or let's call it as F dash to E dash. And what it will cause? It will cause a gyroscopic couple which is in clockwise direction. Okay, so this couple looks like this, which is causing lowering the nose and rising the tail. Okay, so it is just opposite of what we have studied in the beginning. Here it was producing a counterclockwise couple which was rising the nose and lowering the rear, whereas if we just change the axis of rotation of the propeller, things will change. Nose will go down and tail will go up. Okay, so what, and the last situation is this: we are rotating rotor or propeller in a counterclockwise direction, and we are taking a right turn. Okay, and that is just opposite of scenario which is in the figure number C. Okay, opposite. So what we can conclude out of it? We can conclude out of it is the gyroscopic couple depends on the how the in which direction basically the propeller or rotor is rotating, whether it's a clockwise or counterclockwise. If we keep, if the direction of rotation is, let's say, of the axis is left in left side, depending on clockwise direction or counterclockwise direction of rotation of the propeller, situations will change. In one situation nose will go come down, in another situation nose will go up. Okay, in the similar way, if you keep the direction of the propeller constant, that is, let's say, in clockwise direction, depending on whether you are turning towards left or right, the situation will change. In one case nose will go down, tail will go up. In another situation, tail will go down and nose will come up. Okay, so that is what we can see here. Okay, so we have to consider both the things, whether we are changing the axis of rotation towards left or right, that is, you are taking left turn or right turn, and whether the propeller is rotating in clockwise direction or counterclockwise direction. Okay, so both the things matters. Is it clear
Sure.
till this? Yes.
Uh, we if we move in the vertical plane, the most of the aeroplane up or down, is there any gyroscopic couple, sir? Not on the
Okay, so
horizontal plane. If we go either up or down with the nose in the vertical plane, sir.
okay, so yeah, uh yes, so let's think on it. Yeah, it should create in that situation also.
But in case of a helicopter, if we take left or right turn, there was no gyroscopic couple, sir.
Yeah, I will explain. Uh, Basically, the reason behind, um, let's say, when in which situation gyroscopic couple will come or in which situation gyroscopic couple will not come is like, um, uh, let's say, if the axis of the rolling and uh, is parallel, basically you can, or you can say For example, let me just I'll explain first to you the a ship's part. In that part, your question will be covered. Okay, because in ships, uh, generally in aeroplanes, once we reach certain height, we just fly at that particular height. Okay, we don't go up or down. We just fly, then take a constant height, and then go down. But in ships, what happens is, let's say, ship has to go
Yes,
through
sir.
the ship has to go through, let's say, some waves. So in some cases, will go up or down. So in that case, that we call it as a pitching. So in that case, some gyroscopic couple will come into the picture. Okay. Um, so I'll go to that example first and then come back to this. Then things will be more clear to you. Okay. So write down heading first: gyroscopic effect on naval ships. Okay. So here I'll first introduce you some terms. Okay. Um, bow is, you can say, front end of the ship. Stern or aft, you can say, is rear end of the stiff. Okay. Then port is left side of the ship when you looking from the stern. Okay. And starboard is the right hand side of the ship when you're looking from the stern. Steering is the motion in left hand right side direction, as our four-wheeler steering. If you can turn left or turn right. Okay. Pitching is the motion. Either your ship will the bow of the ship can go up or down. That is rising and lowering of the ship is, you can call it as a pitching. And another one is, let's say, uh, rolling motion. Okay, here rolling motion, that the ship can, let's say, ship can tilt in right direction or left direction. Okay. uh, in which situation you can think of, let's say, uh, gyroscopic couple will form, yeah, out of this situation. So we have three motion: steering. Okay. Steering in the sense either turning left or right. Second one is pitching, either rising or lowering. Okay. And third one is rolling. Did you get my question? And now same example, um, like we have these terms here in aeroplanes also. Like we can compare this thing now. Either you can take turn left or right, that you can call it as steering, same as steering here. And let's say pitching here is like going up and down. And the rolling part, we generally we don't know, or we don't do in we just do it in fighter planes. Out of the, in this situation, in which situation you can think of, let's say, sorry, you can think of gyroscopic couple, in which situation it will form? Look at the definition first of what we have studied, and then you will clearly understand what the definition says. What the definition says? Definition says that if the axis of the spinning of the rotating body is given an angular motion, in case of steering, are we changing the axis of rotation? Yes, correct. We are changing the axis of rotation by some angle. In pitching, are we doing the same? Yes. So in these two situations, we can think of uh, a gyroscopic effect. But in case of let's say um, rolling motion, are we changing the axis of the rotation? No, because here the axis of rolling of the ship and the rotor is like says in the same direction. So in that case, you cannot basically expect that the gyroscopic effect will come into the picture. Okay. Now, if I come back to the example of aeroplane, so can you think of, let's say now, if you take a left turn on right turn, your axis of rotation is changing, right? Uh, your axis of rotation is changing. Do you agree? We have already studied, and now, if let's say if you do let's say um, pitching action here, okay. So if you are uh, move, if you are taking takeoff or landing situation, okay. Um, there are other ways to they use other features to avoid this, but in those situation also you can expect a little bit difference or little bit change. They don't suddenly let's say go down or go up, okay. Slowly um, they'll come down, or slowly they'll go up. So in those situations also there is a slight change in the, you can say, axis of the rotation of the rotor, and a slight gyroscopic um, effect will be there, but that is compensated by other features in aeroplane that we don't see. That's why we don't see it. Even um, if you take a left turn or right turn, we don't notice it if it is not taken suddenly. Okay, depending on how sudden, let's say, uh, we can say uh, change in the direction of the um, axis of rotation we do, uh, the gyroscopic effect will depend. Okay, is it clear till this? Because you can clearly see the torque value is depending on the omega p, that is change in delta theta with respect to dt. First of all, how fast you are driving, and second one is how fast you are turning. Both the things will affect the torque. Okay, so if you are driving slow, on top of that, if you are turning slow, you may not feel this torque much. Okay, much torque, you can easily handle the vehicle, or let's say ship or something. But if you are driving fast, on top of that you are turning fast, then in that case this effect will be more, and there is a chance of, let's say, all these situations we are seeing studying. Is it clear till this? Yeah. uh, so at least here you understood that in steering we don't see a gyroscopic, sorry, in rolling we don't see a gyroscopic um, effect. Let's study in this steering situation. In steering situation, if you are taking a left turn, okay, if you are taking left turn, O to A is the initial vector, taking a left turn, O to B your um, new vector, AB is your uh, active couple, and B dash A dash is your reactive couple. Because of this reactive couple, you can clearly see it's a counterclockwise direction. Counterclockwise direction means like this. It will, you can clearly see it will rise the bow and the lower the stern. Okay, so whenever you are taking a left turn, depending on your omega and omega p, you will feel how much is the bow, or the bow is lifting up and stern is going down. And it is opposite in the case of right turn. When you do right steering, O to C is initial vector after taking a right turn by delta theta angle. O to D is a new vector. CD is your active torque. D dash C dash is your reactive torque, which is clockwise in nature. Clockwise in nature in the sense it is like this, which is causing lowering the bow and upward direction of the stern. Okay. Is it clear about the steering? Steering is pretty clear. We have already studied some example of the aeroplane, so it is very straightforward to understand. Now let's try to understand this pitching situation, okay, which is little new. In pitching situation, I'm showing here, okay, these two diagrams are for pitching. The first diagram is bow rising, means you are let's say assume like your ship is, let's say, bow is up in upward, blue bow is up and stern is down, like that ship is moving. Okay. So if that is the situation, OA was initial vector and OB is a new vector. So O to A is active couple and B dash to A dash is a reactive torque or couple, you can say. Then it is how it is. It is counterclockwise direction. Okay. It is counterclockwise direction. What we can understood from this. So it is in counterclockwise direction like this. No, sorry. Just a minute. No, it is a clockwise direction. Sorry, it is clockwise direction, right? So it is clockwise direction in the sense the if you look from the up, okay, when bow is rising, reaction couple is clockwise. If you look from the top side, okay, view from the top side, and what the effect of it is shift will slightly move towards right because couple is clockwise, so our ship will slightly move towards right or towards the starboard side. Okay. Second situation, O to C is initial vector and let's say bow is lowered. Okay, bow is lowered. So in that case, C to D is your active torque, D dash to C dash is a reactive torque. So the couple here is counterclockwise. Okay, if you view from the top, the couple here is counterclockwise. Okay, you're viewing, try to understand, you're viewing from this, so it is counterclockwise like this if you look from here. Okay, so counterclockwise means in this direction, it means ship will turn towards left towards the port side. Okay. I hope it's clear. Why this is happening? Because we are changing the axis of the spin. Okay. In the rolling case, that is not happening because we are not changing the axis of the spin. That is to be noted. Yeah. Okay. The next example I would like to give is for the automobile. So write down stability of the automobile heading or gyroscopic effect in automobile. In automobile, things are little different because it's not just a gyroscope, like there it's moving on, let's say There are four wheels. First of all, we'll try to understand in detail how say, whenever we're taking left turn or right turn, how centrifugal force is applied, how the centrifugal couple basically act, how this uh, gyroscopic effect will gyroscopic couple will act and all. Okay, uh, and how the reaction is because of the weight of the overall automobile. That is what we'll study. Okay, so let's consider four-wheeler first, and then we'll move towards a two-wheeler example. So it's about the four-wheeler now. We have four wheels: one, two, three, and four. Okay, one, two, three, and four. Okay. Um, when we say our automobile is stable, okay, or running stable, whenever the four-wheel none of the wheel out of this four is lifted off the ground, then we can say that um, the vehicle is basically stable whenever we are taking a turn. Okay, our one none of the wheels should lift up, and as long as this condition is fulfilled, the vertical reaction on the ground at any on the any wheel, you can say, is positive or upward. Then only it is possible that uh, this condition is, you can say, fulfilled. Okay, so this condition is fulfilled as long as vertical reaction on the ground on any of this wheel is positive or in upward direction. Which condition? That none of the wheel should be lifted off the ground. Now, if you look into this figure, you can clearly see four wheels are there, and let's say overall mass of this vehicle is m. Then mg by 4 is a weight on each wheel. Do you agree? So each wheel, to each wheel, the mg by 4 um, or on each wheel mg by 4 wheel, let's say weight will act. So that weight will go from wheel towards ground. So basically from the reaction from the ground also you'll get some reaction on each wheel, and that is again the mg by 4. Okay, so first reaction you are getting, let's say rw 1, 2, 3, 4 is is a reaction on each wheel because of the weight of the vehicle, and that is nothing but the mg by 4. Is it clear till this? Okay, so first of all, first reaction is because of the weight. Now let's try to bring the gyroscopic couple into this and the centrifugal couple into this. Starting with the gyroscopic couple. Okay, so we have four wheels. I omega omega p is a gyroscopic torque. Okay, torque. But if you have four wheels, 4 times I omega omega p will be your gyroscopic couple, we can say. And I can write it as 4I into omega is nothing but the v by r. V is the velocity, r is the radius, okay, of the radius of the wheel, and the v is the velocity, and r is the radius of the curvature. Okay, so this is your, whenever you are taking a left turn, what is your radius of the curvature? Is that is capital R. Okay, and small r is your radius of the wheel. Are you getting? V is the linear velocity of the vehicle, capital R is the radius of the curvature, small r is the radius of the wheel. So what is your omega? Omega is your angular velocity of wheel. I can write it as a V by R. And omega P was angular velocity of precision. It is change in the direction. So it is capital V by R, I can say, because R is your radius of curvature. I hope you understood till this. And let's say this is on the wheel itself. Another rotating part will be, let's say we are considering engine also here. Okay. So let's call this as a C W, basically couple coming from the wheel. Couple coming from the engine will be CE, and let's call it as IE. Couple coming from the engine will be equal to IE omega engine into omega P. You can further write it as IE gearbox ratio times omega of the wheel into omega P. I can write it like this. Okay, because gearbox ratio is nothing but the gearbox ratio G is nothing but the omega E by omega. Omega is the rotation of the wheel itself. Okay. Yeah. So total gyroscopic couple will be CG, I can say as CW plus CE. Okay. Plus or minus. Because plus sign you will use when engine parts rotating the same direction as that of wheel, and negative will be whenever engine rotates in the opposite direction of the wheel. Okay. So plus or minus, I would say. CG. So now let's assume whether the depending on left turn, let's say if vehicle is taking left turn, what will happen? If vehicle is taking left turn, OA is our initial vector. After left turn, OB will be our next vector. AB is active torque, and B dash A dash will be our reactive torque, which is clockwise direction. So it is like this. If you look from the top, it is like this. Are you following?
No, sir, it was raising the front part, sir, actually.
No, it's not about front and back. It's about right and left. Uh, right and left. Try to think on this. Okay. Your axis of rotation is this. Okay. So your rotor is not here. This is not your rotor. Your rotor is
Yeah,
here.
I understood, sir. Understood.
Yeah. Okay. So your rotor is on left hand ends. Okay, here. So I will repeat. If vehicle is taking left turn, gyroscopic effect on it is clockwise. If you view from the rear side, okay, if you look from this side, it is look like this. Okay. So this is your gyroscopic couple. The reaction couple will be viewed, you can say, equal and opposite to the forces on the inner and outer wheel. So because of this couple, what will happen? A reaction also will get from ground on the wheels. And how it will look like? This, your couple is like this, gyroscopic couple. Because of that, reaction you will get on the wheels, which is in counterclockwise direction. And that's why on outer wheels, you can clearly see here, forces on outer wheels are CG by W. Okay, CG by W in upward direction. Okay, try to understand this RG, why here it is in upward, and here RG, why it is in downward direction. Because we are writing here reaction forces on outer and inner wheels. Okay, so we have 4 wheels, and out of which 2 are on right upward, on 2 are on right side and 2 are on left side. So I would say forces on each outer wheel will be CG, that is total gyroscopic couple, divided by 2 times W. This will be in the upward direction. Sorry, not forces, this is a reaction. Force will be in downward direction. Okay, reaction will be in upward direction. Okay, because we are writing the reactions on the wheel, and reaction on each inner wheel is same, CG by 2W, but when in downward direction. Okay, whenever you are taking a left turn. So that is the first part of this. Okay, gyroscopic couple. If you take a right turn, then things will be opposite. Okay, so let's not consider it now. You know it. Think that if you take a left turn and right turn, things will become opposite of each other. So let's focus. We are assuming a left turn itself. So RW is pretty clear. All are upward because it is coming from weight. And RG also, I feel it's clear to you now. That is coming from the gyroscopic couple. That is the reaction on the wheels coming from the because of the gyroscopic effect. Upward on the rear wheels or outer wheels, and the inner on the and downward on the inner wheels. Yeah. And the next one is centrifugal couple. Okay, I will write on the next page. Third one is centrifugal couple. Okay, centrifugal couple. So whenever your vehicle is moved on a curved path, centrifugal force also acts on the vehicle in the outward direction. You know, mr omega square or mv square by r is the value of the centrifugal force. Okay, where capital R is the radius of the gyration, v is the linear velocity of the vehicle, and m is the mass of the vehicle. Okay, so what will happen because of this? Think of this, because of the centrifugal couple, the overturning will happen.
The outer will subjected to the upward reaction from the ground, sir.
Yes, you are talking about the reaction. It's correct. The force would tend to overturn the vehicle outwards. So basically, let's say in reality, what happens is you are taking a left turn. Okay, so because of this, your vehicle will overturn in this direction. Correct. But if you don't use this banking and all, banking of road and all, okay. Now, and we know we do banking in order to avoid it, so we will not go into that detail in this example. We know that because of the centrifugal force, vehicle will the centrifugal force will tends to overturn the vehicle in outward direction. Okay, you are calling it as a overturning couple. So force on each outer wheel will be, so your vehicle will overturn like this. Okay, so okay, it's turning on left hand side, it will overturn like this. So the force will act downward and this will go up, this will overturn like this. Okay, try to understand. So this thing will go up, left side will go up, and right side will go down. Then we'll say it as a overturning on the overturning outwards. Okay. Now this is about the forces. What about the reactions? Reaction on each inner wheel. So if it is going up, reaction will be downward. If it is going down, reaction will be upward. So I would say reaction on ground, reaction of ground on each inner wheel will be centrifugal couple, okay, divided by 2W, okay, and that is in the downward direction. And reaction on each outer wheel will be Cc by 2W. This is upward. Okay, so you can clearly see here, outer wheel is upward Cc, inner wheel is downward. Okay, so this is how these all directions are specified. Yeah. What is the Cc? Cc is the uh, Cc is your centrifugal couple. We have studied centrifugal force, that is mv square by r, and let's say mv square by r into h. If you multiply to it, it will form a couple because this fc is in left hand side direction, this fc is in right hand side direction. So centrifugal force into cup h will give you the centrifugal couple. Okay, mv square by r into h will give you the cc. This is centrifugal force and fc, and this is h is the distance between them. Okay, so I hope here you will get clear idea what is fc and h. G is your center of gravity, and h is distance from ground towards the center of gravity. That's why fc into h will be the centrifugal couple. Okay. Yeah. So now if you, let's say, combine all of them, how it will look like. Let me just consolidate it in this on one slide. Let's say I'll consolidate here. Vertical reaction on each outer wheel will be, everything was upward, right? So it's rg plus gyroscopic plus rc plus rw. Reaction due to weight is w by 4. Okay. Then the next is gyroscopic. I would say it as cg by 2w, and centrifugal is cc by 2w. Okay. Similarly, vertical reaction on each inner wheel. Okay. Sorry. Will be, sorry. Yep. it is W by 4 minus CG by 2W minus CC by 2W. Okay. This also has, all of them has to upward. Okay. Everything has to be upward. Then only we can make sure that there will be none of the wheel basically is lifted up. Okay. This we have to make sure. Now we can clearly see in, I'll just go to this main diagram. You can clearly see all RG, RC and RW all are in upward direction. So on outer wheel we don't have any risk. It is observed that chances of the reaction of the ground on the outer wheels are never be in downward direction. But in, if you consider the leftward wheels, okay, wheel number 1 and wheel number 3, there can be a chance, okay, there it is possible that the reaction of the ground may or may not be upward. Okay, so why? Because two reactions are in downward direction, that is Rg and Rc, and only Rw is upward. So if Rw is greater than Rg and Rc, then you can say that you can avoid lifting of any of the wheel from the ground. Okay, and you can make sure that your vehicle is stable. Is it clear? Are you following it? Because let me show here. See, if this is more than these two, W, this is capital W, okay, this is a weight. The reaction because of the weight at each wheel, if it is more than or equal to sum of gyroscopic reaction and reaction coming from centrifugal force, then only you can make sure that the overall reaction is upward, which is positive. Okay, otherwise the reaction, if it is downward, it means the wheel is already lifted up from the ground and your vehicle will not be stable in that case. Are you following? So the weight of the vehicle also important okay, for more stability. Okay, the you might have used some cars. Okay, let's say a simple example, if generally we can see Maruti Suzuki cars are like little bit light compared to Tata cars. Okay, and in both the cars you can feel the difference in stability. Okay, there is difference in weight. Okay, weight of generally Tata cars is like more, you can feel a difference in stability. Okay, there are other effects of it, but um, at least one point I would like to highlight is weight is also one of the factor. um, you can feel if more the lighter is the vehicle, okay, um, there is a more chance of, let's say, non-stability. Yeah, good example in the auto. If you sit in auto and if auto drivers drives fastly and taking turns, okay, um, fastly, then obviously um, it will, you can clearly see it's not stably running. And also width also matters, because in both the cases CG by 2W and CC by 2W, okay, where it is uh, width of the vehicle, you can say. Okay, so width also matter, um, because um, width is like a um, not only uh, you can see here it is inversely proportional. Okay, so width also plays an important role in calculating the reaction. So all of these are, let's say, points you should note. So main thing here is for inner wheel. Okay, uh, your weight reaction should be higher than the other two. Okay, that is for sure. So this exam, or this is for the, this is what you should know. For outer wheels, you don't have to worry, all reactions are in upward direction. Okay, clear? Okay, we got one question here. If we decrease width and height to make it stable. Okay, so basically stability is what we are saying is in terms of turning. Okay, whenever we say stability of the vehicle is not just about the stability in turning, but stability in driving also. So there are different factors for stability. We'll not go into the details. I'm just talking about the stability in turning. Okay, whenever you are taking a turn, um, what factors it will affect. Okay, so whenever you take turn, three kind of because if you don't take turn, the other two stuff will not come into the picture. Okay, so you don't have to worry about it. So whenever you are taking turn, in those situations only you can see that the gyroscopic and centrifugal um, couples will form and it will cause the reaction. Okay, as you increase the height, okay, if your let's say wheels are like um, having higher diameter, more diameter wheels, then basically your gravity CG of the vehicle will shift up, and basically that will cause higher CC. That is also not good. Okay, um, so because if you increase the CC, obviously CC by 2W, that is reaction force coming from the centrifugal couple will increase. Okay, that is one part, and W is this. Okay, width in between the reactions. If you increase the W, that's good. Okay, if you reduce the W, what will happen? The chances of let's say if you reduce the W, obviously CC by 2W will, or CG by 2W will increase, and your couple due to gyroscopic and centrifugal will move. Okay, so basically if you reduce the width, your stability is gonna reduce, and your, if you increase the height, your stability is also reducing. Are you following it? Sorry, I'll repeat. If you increase the h here, okay, h in the sense what we are increasing, center of gravity you are increasing from the height. So let's say a taller, let's say a larger and larger wheels if you are putting unnecessarily. Okay, let's say diameter is required is, let's say for example 180 um, 180 centimeter, but you are, let's say, putting 3 300 centimeter and more than that unnecessarily. So because of that, what will happen is your CC will increase, because CC will be um, centrifugal force into H. So as CC increases, the reaction because of the centrifugal couple will increase. Okay, and W is, so if H increases, CC will increase. Okay, that is one part, and because of that, this part will increase. Okay, do you agree? Second thing, if W is increasing, this will decrease. So width increases, that is good. But if you reduce the width, what will happen? This whole part will again increase. Not only this, but also this. So these two parts will increase. So reducing weight is also not good. Reducing width is also not good. Are you following it now? Do you understand the use of width and height, like how it is affecting the reactions? Okay, so you just calculate the RG and RC. Just check the effect of width and effect of height on let's say RC or RG. That's all. That will help you to understand the how the variation of these parameters affect the stability of the vehicle. Yep. Okay. The last point I would like to take here, we have some more time. We can cover it and end this topic. Is stability of two wheelers. Okay, two-wheel vehicle. In two wheelers, similar things you can expect what we have studied in the four wheeler. Um, but here it is very easy to neutralize the effect of overturning because you can handle the vehicle easily in two wheeler. Okay, so let's take a situation that you are taking a left turn again. So OA is your initial vector and OB is your final vector. A to B is your active couple and B dash to A dash is your um, reactive gyroscopic couple. Okay, B dash to A dash is reactive gyroscopic couple and it's creating a clockwise direction. Okay, so it is this is clockwise basically. I hope it's clear till this. Okay, I'll repeat. We have vehicle who is taking left turn here. Okay, and whenever we are taking a left turn, generally we incline our wheels or incline whole vehicle by certain angle theta. We don't directly take left turn like this. Okay, we turn vehicle, okay, like by some angle theta. Let's say theta is with respect to vertical. Let's call it as the angle of heel. It is inclination with respect to the vertical or equilibrium. V is the linear velocity of vehicle running on the track. Small r is the, let's say, velocity. Small r is the radius of the wheel. Capital R is the radius of track or curvature. Okay, so this terminology you know. I omega is moment of inertia of each wheel. I is inertia of engine parts. M is the mass of the vehicle and the rider. So write down these things. This is the radius of curvature or track. This is radius of wheel. Moment of inertia. Of each wheel. This is moment of inertia of engine parts. Okay, this is total mass. That is vehicle plus rider. Omega W is angular velocity of wheel. Omega E angular velocity of engine part. G is the gearbox ratio. H is the height of the center of mass of vehicle and the rider from the ground, you can say. Okay, is center of mass of vehicle and the rider. Theta is, you can say, let's call it a CG. Okay, theta is inclination as a angle of heel, you can say. Yeah, I hope it's clear till this. Yeah. Gearbox ratio. So what is the gyroscopic couple in this case? Gyroscopic couple will be, we have two wheels, so 2 times I omega, and I of wheel, omega of wheel, plus we have one engine, I of engine, gearbox ratio times omega of wheel, because omega of engine is nothing but the omega of wheel into gearbox ratio into cos of theta times omega p. Okay, because I omega p is our gyroscopic torque or gyroscopic couple. Okay, now let's take some terms common here. 2 times I omega plus I e omega w will, sorry, iw plus I e, 2 times iw plus I e, and g is also there, so I should write g as well. Omega w I'm taking out, which is v by r. Omega p is v by capital R, so it is v square by r into r cos of theta. Okay, this is your gyroscopic couple. Yep. And so in two-wheelers also you will feel the overturning, right? So sorry, you will feel the centrifugal force, and that is again m square by r into h cos theta. So this is one thing, and overturning. This is gyroscopic couple, I would say. Okay, then we have overturning couple due to centrifugal force. How it will look like? It is m v square by r into h cos theta. Okay, m v square by r into h cos theta. Now, what is total overturning couple? The vehicle is overturning not just because of the gyroscopic couple, but also because of the centrifugal force. So sum of these two will give you the total overturning couple, that is 2i omega, sorry, 2iw, that is inertia of the wheel plus gearbox ratio times the inertia of engine, v square by r into r cos of theta plus mv square by r h times cos of theta. From all these things you can take v square by r common and write the remaining stuff. So I'll go here on this slide and write down here total overturning couple would be equal to v square by r 2 times moment of inertia of the wheel plus gearbox ratio times the moment of inertia of the engine parts times small r plus m into h cos of theta. Do you agree till this? This is what we can say, this total overturning couple. So when we'll say that two-wheeler will be balanced, so whenever in this case it will not overturn if you put appropriate slope to the road itself. Okay, if you use proper let's say um, or basically I would say whenever you basically increase this theta a lot. Okay, let's forget about road. Okay, if you are driving a vehicle and if you increase this theta a lot, there is a chance that the vehicle will skid. Okay, in order to avoid that skid, what you can say, balancing couple due to weight of the vehicle. Okay, uh, you know that this was a diagram. Weight of the couple, you can say here mg into h sine theta, that will be the weight couple. Mg into h sine of theta has to be equal to this v square by r times 2iw plus gi divided by r plus mh times cos of theta. This will be the relation for the equilibrium. Okay, this is for the balancing of the two-wheeler. Okay, whatever the couple coming because of a self weight should balance the total overturning couple, then only you can say that you can avoid your vehicle from the skidding. From this you can calculate the theta. Okay, from this you can calculate theta. That will say that this should be the value of theta. You should not cross. Okay, so from this relation, angle of heel can be determined to avoid skidding. Okay, is it clear till this? Okay, just to consolidate what we have studied in this chapter, we understood that the gyroscopic effect mainly comes whenever we change the axis of spinning or rotating body. Okay, because of this, the axis will not just go into the applied direction, but it moves in the third direction. Okay, because of the reactive gyroscopic couple. We also understood how we can evaluate the angular acceleration if omega is changing and if omega is not changing. How we can calculate the gyroscopic torque, how the effect looks like in the aeroplanes, naval ships, automobiles, that is four-wheelers and two-wheelers, and how we decide the stability in both the situations. Okay, so this is what you should know as far as the theoretical and the formulas for from this chapter is concerned. Okay, I hope it's clear to all of you. You can just go through this recording once again or these slides. You will be able to understand it. Okay, and that will be very easy when we start solving questions. Okay. Okay, do you have any other doubt? Okay, then thank you all for joining this class, and let's meet again tomorrow with a new chapter. Thank you all. Bye. Good night.